Advanced Engineering Physics. Unit 1. Crystallography and Materials Characterization. Introduction to crystallography. Matter is made up of atoms, ions, or molecules. These particles are extremely small, so matter appears continuous to the naked eye. But at the microscopic level, it has a definite structure. When a substance cools below its freezing point, the kinetic energy of its particles decreases. In a crystal, the particles become fixed in a regular, repeating three-dimensional pattern. This ordered arrangement forms a crystalline solid. A crystal is defined as an anisotropic, homogeneous body made up of atoms, ions, or molecules arranged in a three-dimensional periodic order. The word anisotropic means that the physical properties of the crystal may change with direction. For example, hardness, thermal conductivity, and electrical behavior may be different along different directions in the crystal. This is different from amorphous solids, such as glass. In amorphous materials, the atoms do not have a regular long-range periodic arrangement. These materials are formed when a molten substance cools too quickly for the atoms to arrange themselves into a crystal structure. Amorphous solids behave like frozen, highly viscous liquids and usually have higher internal energy than crystalline solids. Crystals and amorphous solids also differ in their thermal behavior. Crystals have a sharp and definite melting point. Amorphous solids do not melt sharply. Instead, they soften gradually over a range of temperatures. Their X-ray behavior is also different. Crystals produce sharp X-ray diffraction patterns because of their regular atomic order, while amorphous solids do not produce sharp diffraction peaks. Now, let us understand the concept of a space lattice. A space lattice, or point lattice, is a three-dimensional periodic arrangement of mathematical points in space. It is an abstract mathematical model used to describe crystal structure. A real crystal has finite size, but a space lattice is imagined to extend infinitely in all directions. The periodic nature of a lattice is described by three translation vectors, usually written as A1, A2, and A3. If the position of a point is represented by R, then an equivalent point in the lattice is given by R' equals R plus U1, A1, plus U2, A2, plus U3, A3, where U1, U2, and U3 are integers. This means the lattice repeats itself after fixed intervals in space. Next comes the basis. The basis is the group of atoms, ions, or molecules attached to each lattice point. Every basis in the crystal is identical in composition, arrangement, and orientation. The basis gives physical meaning to the mathematical lattice. In other words, the lattice tells us where the repeating points are, and the basis tells us what is attached to each point. The position of an atom in the basis can be expressed relative to its lattice point using fractional coordinates along the lattice vectors. These coordinates are usually written as xj, yj, and zj, and they lie between 0 and 1. This leads to one of the most important relations in crystallography. Lattice plus basis equals crystal structure. A crystal structure is formed when the same basis is placed at every equivalent lattice point. Since the lattice points repeat periodically, the basis also repeats periodically, creating the full crystal. Now, let us discuss the unit cell. A unit cell is a parallelepiped defined by the three translation vectors. It is the smallest repeating building block that can fill all space by translation alone. The entire crystal can be generated by repeating the unit cell again and again in 3 dimensions. A special type of unit cell is the primitive cell. A primitive cell has the minimum possible volume and contains exactly 1 lattice point. For example, if a cell has lattice points only at its 8 corners, each corner is shared by 8 neighboring cells. So the total contribution is 1 lattice point. Another way to construct a primitive cell is the Wigner-Zeitz cell. It is formed by drawing lines from one lattice point to nearby lattice points and then drawing perpendicular bisectors at their midpoints. The region enclosed in this way gives the smallest volume around that lattice point. Any unit cell is completely defined by 6 lattice parameters. These are the 3 edge lengths, A0, D0, and C0, and the 3 interaxial angles, alpha, beta, and gamma. Alpha is the angle between B and C, beta is the angle between A and C, and gamma is the angle between A and B. The volume of a primitive unit cell is given by the scalar triple product. Vc equals the magnitude of a 1.A2 cross A3. This formula gives the exact volume enclosed by the 3 translation vectors. In summary, crystallography begins with the idea of periodic atomic arrangement. The lattice provides the geometric framework, the basis provides the actual atoms, and together they form the crystal structure. The unit cell is the repeating building block, and the lattice parameters completely define its geometry.